Okay, we're in chapter 10.1 of Barnett, and it's the introduction to limits. This chapter 10, limits and the derivative, is one of the key concepts of calculus and one of the more important things that we're going to look at in our course. So keep that in mind as we go through chapter 10. There are several learning objectives there to recall what are functions and graphs, and then to look at the idea of a limit. Okay, so we'll do that through several videos. Okay, so just to remind you, the graph of a function is the graph of the set of all ordered pairs that satisfy the function. Remember, ordered pairs are the x and y input and output that you obtain from the function, right? So as an example, look at the following graph and table that represent the function f of x equals 2x minus 1. Okay, so what happens here is I can create a bunch of ordered pairs by picking values of x, like negative 2, plugging them into the function's rule, 2x minus 1, and that would give me an output, or a y. And then I get an xy ordered pair. Okay, I can continue this over and over. I could keep picking points for x at random, whatever numbers I want. And let's see, what happens when we plug in 2? We're going to use this number on the next slide. When we plug in 2, we get 2 times 2, which is 4, minus 1, so we get 3. So the point 2 comma 3 is on the graph of the function. When we plug in 3, we get 2 times 3, which is 6, minus 1 is 5. So once again, we can conclude 3 comma 5 is on the graph of the function. And here is 3 comma 5. So you see the collection of all these ordered pairs, the set of all these ordered pairs, 3 comma 5, 2 comma 3, 1 comma 1. All of this gives me 0, negative 1, right? We have another one here, don't forget. And there's a bunch of others. There's some in between that are not even described in the table. But the important part is to point out that the collection of all these is what we call the graph of the function f. Okay, so let's jump to this next idea of a limit using the graph. Well, using our function f of x equals 2x minus 1, let's examine what happens near x equals to 2 through the following chart. So what's happening in this chart is we have different values of x, and as you could tell, we have x equals to 2 right over here. And we're looking at values that are really, really close to 2 from both sides of 2. What do I mean from both sides of 2? I mean to the left of 2 and to the right of 2. So if you notice, if I start at 1.5, on a real number line, here's 2, here's 1.5. 1.5 is to the left of 2. Then what I do is I evaluate my function at 1.5, my f of x. And then I say to myself, well, I can get closer to 2 from the left. So I pick 1.9. Once again, I evaluate the function at 1.9 and I get 2.8. And then I say to myself, well, you know what? I can get even closer to x equals to 2. I can pick 1.99. And let's see what happens when x is 1.99. Go back to this function here, plug in 1.99 for x, and you get 2.98 as the input. And then what's happening is we're getting closer and closer to 2. Let's say this is 1.99, right? And obviously I'm exaggerating my scale here just so you could see the points. But I'm getting closer and closer to 2 from the left side of 2 without ever hitting it, okay? Without ever actually calculating what's happening at 2. Then I do the same thing from the right-hand side. I start somewhere really close to 2, like 2.001. And I calculate the value of f of x there. Then I look at 2.01, again exaggerating the scale a little bit. Then I look at 2.1, and then I look at 2.5. So as I get further and further away, I see what's happening here. Well, again, I calculate the f of x values, and what do you notice? You should notice that the closer and closer you are to 2, f of x approaches 3. It gets closer and closer to the value 3. Now, we knew from the previous slide that at 2, the f of x value is indeed 3. But when we talk about limits, we're never really interested about what's happening at the point x equals to 2. We're interested about what's happening near the point x equals to 2. So we say as x approaches 2, which really means as x gets closer and closer to 2, or as x is near 2. Okay, we can now formally define out what a limit is, sort of generalizing this example. Here's the definition. We write the limit, LIM stands for limit, as x approaches c of f of x to equal L, or we say as x approaches c, then f of x approaches L, right? This arrow means approaches. And what does that mean? Well, when does that occur? When does it take place? That takes place if the functional value of f of x is close to the single real number L whenever x is close to but not equal to c on either side of c. So as you saw in the previous example, we could have said here that the limit as x approaches 2 of our function 2x minus 1, f of x, right? That was our function, f of x. I could have said that that limit was 3, because the closer and closer the inputs got to 2, the closer and closer the outputs got to the number 3, as you could see in our chart. So that's what we mean by x approaches 2, f of x approaches 3. And here it is written in the formal definition. Whenever the values of x get closer and closer to some number c, then the values of f of x get closer and closer to this value L. Another example that we have the graph of here on this slide is, in limit notation, we have the limit as x approaches 2, here is x equals to 2, of the function x plus 2, which you see graphed here. That limit is equal to 4, according to our example. And let's see visually, looking at a graph, if that's the case. In fact, let me zoom in here, just so that you could get a good look at this graph. Notice, as we pick values of x that get closer and closer to 2, and we try to see, based on our graph, what are their y values? Well, notice their y values are getting closer and closer to 4. Okay? Then we do the same thing on the right side of 2. If we look at to the right of 2, here is 3 values to the right of 2. And once again, notice that these values are getting closer and closer to 2 as you go from right to left, except that's the catch, right? If you go away from 2, obviously, then you're going further away from 4 on the output axis here, on the f of x axis. But the closer and closer you are to 2 from the left and right, the closer and closer you are to 4 on the y axis.